Good morning, gentlemen. How are we doing this fine Friday morning? It's the last day of the semester. Normally that would entail like donuts or cookies or something of that sort, but thanks coronavirus. Um, yeah, so all right. So today what I wanted to do was basically Q&A, kind of like we did on Wednesday, and just go from there. Um, So Mr. Young, Odysseus Orion, and Mr. Feltz. Who is Odysseus Orion, by the way? I feel like that's Thomas. Um, anyway, um, so so what you guys got? Yeah, what questions can I answer for you? Bueller, Bueller. All right, there we go. 5.4 question number 8. So let us go over to the computer and let us look at 5.4 and see what question number 8 is. Find the average value of the functions on the given interval. Got it. Okay, so let's just remind ourselves, and let's destroy the evidence. Let's just remind ourselves what average value is, first off. It's the integral divided by the length of the interval. Okay. Oh, I'm sorry. I wrote that. Let me go back to the iPad for a second. Um, okay, so that's how we calculate average value. You do the integral of the interval over the entire interval, and then you just divide by the width of the interval. Okay, so way to think of this is the area is the integral, the numerator, and then if we divide by the width, then that gives us a height, and that's sort of the average height of the function. Okay, so Zach, first off, is that how you were calculating these things? Uh, Using that idea basically. And in fact, Zach, what I'm going to do is let me pull up your. I can actually go in and spy on you and see what. Ah, okay. See what you're not. Oh, you'll have to redo it, haha. Okay. All right. Well, let's do part C and make sure that it makes sense. So let me go. Still on the iPad. Let me go to a new page. Your particular numbers were 5 to 13 instead of the 5 to 8. That yes, I see you got 909. Um, uh, so anyway, first off, let's just do this part. Um, And the antiderivative, of course, is x to the fourth over 4 from 5 to 13. So the answer will be, for the integral, we'll have to divide in a minute, will be 13 to the fourth minus 5 to the fourth. And let me just pop open Mathematica real quick and compute that. 13 to the fourth minus 5 to the fourth, because of course that's going to be somewhat big, divided by 4 is 6984. Okay. Um, and then the length of the interval, 13 minus 5, is what, 8? Um, so 6984 divided by 8 is 873 is what you should have got. All right, so how did you get 909, I guess is the question. Um, did you have that, like, symbolically, and then, I mean, it might have been the case that you just fat-fingered it when you calculated whatever 13 to the fourth was. Looks like we're up to 5 or 6 of you guys. Morning, Mr. Hughes, Mr. Gupton. I almost said Mr. Hodges. I don't know why. Sorry. We got 6 viewers and 5 people in chat. Excellent. Because I think maybe I'm one of the 6 viewers, technically. I don't know. Okay. So, oh. I had to, um, I have a bot, to detect any inappropriate language, and it apparently, flagged fat-fingered, because of the latter word in that phrase. Anyway, whoops. Okay, so well, that's good. It's good to remind ourselves what average value was. Uh, yeah. So anyway, okay, what else? 5.4, question 12, C or D. All right, let's go back to 5.4, which is the assignment we're on. Question number 12, C or D. All right. Um, so let's go to the, well, actually, I'll just write it down. Let me just write down D, say, for sake of example, because that one is where you have to pull a trick. In fact, I think I did this last time, or something close to it, but whatever. All right, so this is 5.4D, or sorry, 12D. And I just realized, well, last time, and I think looking at it now, the second part C should have been D. I don't know, yeah, must have typoed it. All right, so we had f of x was equal to the integral from 2 plus cos x to x squared plus 1 of 1 over t dt. All right, so the first trick that we need to do is we need to split this thing, and I'm going to split it at, say, 0. It doesn't actually matter for the purposes of what's going to happen in a minute. So I'll have the integral from 2 plus cos x to 0, and then I'll go from 0 to x squared plus 1, like that. Okay. So the reason I had to split it is because the fundamental theorem requires that one of the bounds, the bottom bound, be a constant. Um, so um, the second integral here, 0 to x squared plus 1, okay, that's cool. But the one that's from 2 plus cos x to 0, I actually want this to be in this form. And then I'll just copy the second integral down. Okay, but if I switch the order of the bounds, then that negates the value of the integral. So I've got to throw a minus sign in front there. Okay. All right, so we cool up to here that the first step is really just to split this integral into two pieces. Um, and also that the 0 that I picked there, I could have literally picked any number for that. I could have just called it A and not even, cared what the value is because it's not going to matter in the next step. All right, so then the fundamental theorem says that we get negative 1 over 2 plus cos x times the derivative of 2 plus cos x plus 1 over x squared plus 1 times the derivative of x squared plus 1. Okay, so that's the fundamental theorem, right? You plug in the top thing, the thing that's a function of x, and then you have to multiply by the derivative of that thing because of the chain rule, right? So this term and this term are chain rule pieces. And then what's the derivative of cosine? It's minus sine. So we'll have a double negative, so that will actually cancel. And then we'll just get this. And then for the second term, we'll just have 2x over x squared plus 1, like so. Okay, so does that make sense? Okay, good. Now, it is worth mentioning, of course, that this particular problem we could have done the other way, which was actually compute the antiderivative and then plug in the stuff, plug in the bounds using the other version of the fundamental theorem and then take the derivative of the result. That would have also worked. The only reason that that would have worked is because the function here, 1 over t, we know it's antiderivative. It's the logarithm. If we didn't know the antiderivative of that thing, then we would be stuck and we would have to approach it with this version of the fundamental theorem. So you guys are, I don't want to say lucky because, of course, nothing about the coronavirus has been lucky. But uh, if we had an actual final, you can bet that I would have made it so that the function there you couldn't actually find an antiderivative of to sort of force your hand. But anyway, uh, you guys are mercifully off the hook for the fundamental theorem, sort of, or well, off the hook for a final. Okay, so does that make sense, Willie? Good. Um, excellent. Um, what else do you guys have? All right, 5.4 question number 7. Let me open that back up. Problems. All right, question numero 7. All right, so Willie, I'll answer this and then we'll go on to these other ones. All right, so Willie, question 7. So which part of question 7 was confusing, Willie? If anything, it probably was either B or C. Yeah, B. Okay. So dx, what you want to think about this is that this is really 1 dx, right? And let me actually rewrite it one more time. I'm going to write it as x to the 0 dx, right? So what's the antiderivative of x to the 0? It's x to the first over 1, which is the same as just x, right? So remember, the derivative of x is 1, or derivative of linear term is a constant, and so when you go the other direction, it's, yeah. So it should be, what, 24, because that'd be 35 minus 11. Um, yeah, so, um, okay. So, yeah, that should have been easy. You probably just made some boo-boo, Willie, because that's super easy. Um, all right, so let's see. Austin, you had number 4 on 6.1. Let me open that up. All right, 6.1, numero 4. Okay, so yes, trig integrals. Let me go over to a fresh page here. So A, we had sine to the 5th x cos x dx. Okay. So we have to make a substitution here. And we've really got kind of two options. Um, so what, Mr. Hughes, did you think you ought to be for this problem? Or for this, yeah, this part of the problem? So this is 6.1, number 4. Oh, what do I mean? We have to do a u substitution, right? So what are we going to make u? We could make it sine, we could make it cosine, we could make it sine to the 5th, although that won't work. Those are really the only three options. So what did you try? Ah, okay. Um, so almost. That means that actually we should make u equal to sine. Okay. So it is true that the derivative of sine is cosine. Okay, but what you want is part of the thing to be the derivative of the rest of the thing. And if we let u equal cosine, here's what would happen. Its derivative is negative sine, and then we would substitute. So we would say this is sine to the 5th x times u times, oop, I'm sorry, I meant this should have been a du. Okay, so that's what would happen if we let u equal cosine x on part A. And, oop, this is sine to the 4th of x. Okay, and here we're stuck. So actually, let me use a better color for this. Okay, there's nothing we can do beyond that. And now we have an integral that involves two letters, x and u, and that just doesn't make sense. Okay, so that was not the substitution to use. So instead, let's try u equals sine x. Okay, the derivative of that is cosine. So dx, or sorry, du, need coffee. Uh, no, actually I meant, sorry. So that's dx, right? Du over cos x, just solve. And so the original integral is going to be, well, we've got sine to the fifth of x times cos x. Dx is du over cos x. The coses cancel. And then sine was what we called u. And so we have u to the fifth du. Okay, that tells us that the substitution was a successful choice because we have nothing involving x left in this integral. Okay, so we Gucci up to there, Austin, and the rest of you. Yeah, okay. Um, all right, well, so then this would be u to the sixth over 6 plus c, and then, of course, what was u? It was sine, like so. Okay, now let's contrast that with part B of this one, which was similar. B had the power on the cosine. Okay, and in this one, you do want to use u equal cos x, not u equals sine. Okay, and the reason is that the cosine is the guy raised to the power, not the sine. Um, so does that make sense, Austin? That um, in this other version, we'd want to do the substitution that you did originally. Okay, makes sense to Willie. Austin, hopefully that makes sense to you too. Let's use u equal cos x this time. So, okay. Well, let's go on. Let's see. Mr. Feltz had 5.2, number 5. All right, so 5.2, numero 5. Ah, yes, a good physics problem. All right, so let me scroll down here. All right, so this is 5.2, number 5. All right, so an object is thrown upward, and the velocity is given by negative 32t plus 61, and then it asks us that it was thrown from an object, or thrown from 50 feet. So basically, like the picture would be that we you know chucked something from a 50-foot building or something like that upwards, and that's my beautiful artwork You can all print it out and put it on your refrigerators. It's so gorgeous. Okay, and so we've got a whole bunch of questions to go here. So the first question is, what's the initial velocity? Well, that's the velocity at time 0, right? So this would be v of 0, and in this case, that's pretty easy to plug in. It's 61, okay? And then this problem also really wants you guys to think carefully, well, this and several of the other problems, think about the units that are involved. So what units are relevant here? Oh, Austin, yeah, let me go back to that. Um, Kind of both, actually, right? So if we go back up, right, notice that cosine is raised to a power, but its derivative is sine. So what I look for when I do a u substitution is I want to find a part of the integral whose derivative is the rest of it. Okay, so if I say let u equal cos x, then I've got a u squared term. And what's the derivative of cos x? Well, it's minus sine x. Now, I've got sine x. The minus, well, that kind of sorts itself out. Um, and yeah. Now, I should also say, I probably said this before, that in some problems there's more than one correct or good choice of u. In other problems, it's sort of forced. Um, and the the thing is that if you pick the wrong u, what will happen is what happened up here at the top there, where you get to a point where not everything is in terms of u and you're sort of stuck. If you get to that point and you're sure that you haven't made some silly boo-boo along the way, then go back and go back and try a different value of u. Um, I should also say that this is kind of an art form, um, and you get a kind of a spidey sense or an intuition as to what would be a good choice for you after you've done more of these problems. So at first, you're going to be kind of stumbling around in the dark, but after you work through a few of them, I think you guys will start to kind of see it. Um, Okay, so there's that. Then let's see what else to mention. Oh, I should also mention that um, it use substitutions is probably one of the hardest things that you learn in Calc 1. Okay, and it was the hardest thing for me when I learned Calc 1. So if you guys will believe it, I actually got a B when I took Calc 1, not an A. And one of the reasons I got a B is because the exam that was over this U substitution stuff, I failed it with a 54. I failed it pretty hardcore. And yeah, that kind of sucked. It didn't quite click with me, and then eventually I figured it out. Um, so this will not necessarily come immediately to you. You have to kind of practice it, and that was, I think, one of the things that I didn't do enough of was I didn't practice. Um, yeah. So Austin, that's probably the best I can give in terms of general hints. Otherwise, you just kind of have to get your hands dirty and try stuff out. Um, so yeah. Okay, so sorry, back to our physics problem. Um, the initial velocity is 61, but what are the units for this? Well, it's a velocity, so it's a distance unit divided by a time unit, and in this particular problem, it's feet is the distance unit, and seconds was the time unit, so it's that. Okay, B asked, what the max velocity is. Okay, so this to some extent may be kind of a trick question. How do we normally maximize a function? We find when the derivative of the function is equal to 0. Okay, um, but the other place where optimization can occur is at an endpoint. All right, now let's kind of think logically here. If I throw something upward at 61 feet per second, 1 second later, is it still going 61 feet per second? No, of course not. It's slowed down because of gravity. So when is the maximum velocity of the object? It's actually the instant that I throw it. And that's because um, the velocity decreases uniformly um, after time 0. And how do I know it decreases uniformly? Well, what's the velocity's derivative? It's that, right? And that's just the gravity in imperial units. So the max velocity here is actually the same as part A. It's 61 feet per second. Now, had this question asked us about the maximum speed, that would have been a different matter. Because what's the path of this thing going to look like? So here's my 50-foot building, and I chuck it upwards. Okay, the speed here when I throw it, and here when it's sort of, if I threw it straight up, it would be like the instant I catch it. The speed is the same at those 2 points, but the velocity is positive here, but negative there because it's going downwards. Okay, so remember, speed is the absolute value of velocity, and but this asked us about velocity, not speed. So velocity has a direction with it, and in this particular case, because we're throwing it sort of straight upwards, the notion of direction for velocity is up or down, plus for up and minus for down, just because, well, that makes sense. Okay, so are we good up to there, Zach? Is that making sense? All right, so let's keep going. So maximum displacement. Well, to talk about displacement, we need to know the position function or the height function. And what that's going to be is the antiderivative of the velocity, right? So if we went from position function to velocity by taking a derivative, we go the other way by taking an antiderivative, and it would be negative 32t squared over 2 plus 61t plus the initial height, which was given to be 50. So I've tacked on the plus 50 there because in this problem, it was given that we chucked it from 50 feet up, not from the ground. Okay, and then of course I could simplify that a little bit, like so. Um, okay, so maximum displacement means we want to find the point at which the object that we've thrown is as far away from where we threw it as possible. And if you think about that, that's going to be whenever it gets to the top of its position. Okay. And when does it get to the top of the thing? It gets there when the velocity is 0. Okay. So what we need to ask is when is v of t equal to 0? And since we have the velocity function, then we get 61 over 32, whatever that is. Okay. In fact, I think 61 is actually prime. Let me look. Yep, it is prime. Okay. So you can't simplify that at all. Okay, so that makes sense, hopefully, right? That the displacement is biggest when the ball is furthest away from where it started. Now, if we waited, so you throw the object up, it eventually comes back down and you catch it. At that moment, when you've caught it, the displacement is zero because it's as if you haven't thrown the thing at all. Yes, it went up and then came back down, but it is in the same position that it started, so its displacement is zero. So the height here, what we want to do is, so displacement is h of t minus h of 0, and we have to subtract off h of 0 because we throw this thing from 50 feet up. And so what we want to do is compute h of 6132 minus 50, because that's h of 0. And so all you've got to do is plug 61/32 into those terms. So this would be what? Negative 16 61/32 squared plus 61 times 61/32, and that's it, because we'd have plus 50 and then minus 50, so those would cancel each other out. And that's going to be some nasty number, whatever you get. What are the units for this? Well, displacement is a distance, so what should the units be? They should be in feet, because that was the distance unit for this problem. Okay. Now, I actually kind of put the cart before the horse here, because, and maybe think of part C and part D here as kind of a package deal. Because notice that in order to find out what the maximum displacement was, we first had to figure out when it occurred. And so the time at which the maximum displacement occurred was the 61/32. And that's the answer to part D. When does the maximum displacement occur? And of course, that being a time quantity is in seconds, because that was the time unit for this problem. Okay, so C and D kind of were a package deal. Also, then, we could compute F here, which is what's the object's maximum height. Well, we know when it achieves the maximum height, it's at this 61/32. So what do you get when you plug that into the height function? It'd be, blah squared plus 61 blah plus 50. That would be, how high it was at the peak. And so that's part F. That really, we could have done that immediately. Okay, now, part E is slightly a trick question. When is the displacement 0? There's actually two answers for that. Okay, what's the obvious answer for when the displacement is 0? Okay, so at what time has the ball gone nowhere? Or effectively nowhere? Yeah, at t equals 0. Okay, so that's the obvious answer, because that's before you've even thrown the thing. So of course it hasn't gone anywhere. Okay, so while that is a valid answer, part E is looking for the other time when the object's displacement is 0. Okay, so what's the non-obvious solution to when the object's displacement is 0? It would be here, when it has come back down and you've caught it. Okay, so yeah, when it lands, exactly. So what we need to do is we need to find when the displacement equals 0, and the displacement we said was this. So for E, when is negative 16t squared plus 61t equal to 0? Well, we can factor So we have t times negative 16t plus 61 equals 0. That gives us t equals 0 or t equals 61 over 16. Okay. So the time when it lands is the 61 over 16. And yeah. Now I should mention that maybe that should have been obvious because compare this with that. Does it make sense that the time at which it lands should be double the time that it takes to get to the peak? Yeah, makes sense, right? Because it takes half the time to get up and then that exact amount of time to come right back down. And so the total time is double the time it takes to get to the peak. Um, so, yeah, so 61 over 16 in seconds, of course, this time. Okay, so does that kind of make sense how we walked through that? And obviously, um, yeah, so with part E, 0 is a valid answer. In fact, I probably should have gone in and said, for what time t bigger than 0 is the displacement 0, just to make sure that there wasn't a confusion there. But yeah, you're right. T equals 0 is a valid answer. It's just not the droid you were looking for. So, yeah. Okay, good. That was a fun one. Anything else? Okay, good. We're up to it's like 10 people in the chat, 6 people watching. We've got Feet, Lurks, Camula, maybe people joining because they think it's a chat channel, not calculus. Okay. Yeah, what other questions do you guys have? Oh, well, of course Dr. Denari is here for the calculus. Yep. No, that's we do that in Calc 2. Um, Eric, not Calc 1. So, all right. Well, guys, if you have no other questions for this morning, anyway, um, let me just say it's been a fun semester. The first half of it was a lot more fun than the second half. That's not y'all's fault, obviously. Um, so, yeah, just a reminder. Basically, the chapter 5 exercises. Um, Oh, okay. Austin, you can do it either way, actually. Um, where you do the U sub and then get the answer. Oh, the traditional way where you plug in. Yeah, it's actually a combination of both. So there's two ways to do definite integrals that have a U substitution. The first is just pretend it's not a definite integral. Find the antiderivative using the U substitution method, replace everything back in terms of x or whatever the original letter was, and then plug in your numbers like before. Uh, or you can convert the numbers. So let me go back to um, let me go back to let's see. This would have been um, yeah, here, Austin. So this problem, which is actually pretty close and ironically to one that we just did earlier, just without the exponent, is you could just pretend that the integral is indefinite, find the antiderivative, and then plug in using the fundamental theorem at the end. The other option is to convert the bounds from x bounds to u bounds, and then you don't have to go back to the original integral. Of course, you end up getting the same answer either way. It doesn't really matter which way you approach it. I pointed out both of them because those of you who go on either to further math or possibly situations in econ, it's useful to have both methods up your sleeve, but you will get the same answer. Either way works. My usual inclination is to do the first version because it means that I'm worrying about the antiderivative and then worrying about the number crunching, so I'm only ever doing one thing at a time, and I find that usually I make fewer mistakes that way, but your mileage may vary. So, um, yeah, so that's fine. All right, so what was I saying? Yeah, it's been a fun semester. Um, like I said, the front half was a bit more fun than the back half. You know, seeing you guys all bright-eyed and bushy-tailed at the basement of Hayes at 8 in the morning, rather than on Twitch. Um, yeah, so hopefully you guys are pretty close to finishing the Chapter 5 exercise pile um, for this afternoon. Let me just look at my grade sheet here and see. Um, yeah, it looks like you guys are pretty close. The Euler's method assignment. Don't forget about that one. The one thing I need to stress with the Euler's method assignment is do not round too much. You know, so when you're computing the numbers for Euler's method, if you round, you're going to get garbage. So you might get, say, the first answer to a question, because this one, those two questions have multiple parts. The more you round, the more likely it is that each subsequent thing is going to get off. And that's because Euler's method, remember, depends on the um, the previous answer influences the next answer. So if you round a little bit too much on the previous answer, it might not be enough to get it wrong, but it's going to be enough to throw off anything that you use from that. So my recommendation would be go out to something ridiculous like 5 or 10 decimal points, or use Excel or Mathematica, kind of the way I showed you guys, to double check your number crunching, to make sure that you're not flubbing the numbers. Um, okay, so well, it's almost 8:50, so so we should probably quit. If you guys, obviously today's the last day of formal classes, but if you guys have questions, then you can always hop on Discord and ask me. I'll try and be on as much as I can over the next few days. And if you've got a question, probably the easiest thing to do is just type in the MAT111 text channel what question you've got, and then if I'm online, then I'll hop into a voice channel, and we can talk about it. And if not, then I'll get to it as whenever I'm back to the computer. Um, all right. Well, good luck with the rest of your finals, whatever those look like for your other classes, and I hope you guys have a great summer. I hope we all can get together again at some point, um, in person. Uh, the college really, really, really wants to have you guys all on campus in the fall like normal. That's our hope that we will be back to that situation. Um, and Because this whole online thing kind of sucked. I mean, it could have been a whole lot worse, obviously. You know, can you imagine if this had happened in 1980 before, you know, before most people had computers at home or before the internet was really a huge thing? Or, yeah, it would have been a complete disaster. Um, we would have had to just cancel spring break and tell everybody to stay put and quarantine you all to campus. But anyway. All right, well, I'll go ahead and end the stream here. It's been fun, and I'll see you guys on Discord, and have a good rest of your day.